Yes, good day, everyone. I am Adedoyin Jeremiah. I'm known as Presidomath or Jerry Springer. So we want to continue from where we stopped in the first class of Lebesgue Measure and Integration. In the first class, we have introduced what we call the Lebesgue outer measure, and as well as its properties. We also went further to prove all of its properties as well. So now we want to continue with, we want to define Lebesgue measurable or Lebesgue measurable set. We want to define Lebesgue measurable set. Now, I want to define Lebesgue measurable. A set E in R, a set E, a subset of R. Since I'm working in R, I'm in R. A set E in R, the space I'm working on is on R. Is said to be Lebesgue measurable if for any test set you take in R, for any tau or any t you take in R, for any set you take in R, or we can say subset of R, the outer measure of t is equal to the outer measure of E intersection t plus the outer measure of t intersection E complement. Let me write this as d intersection E. So, if this is satisfied, then we say that the set E is measurable or is Lebesgue measurable. Or we say E is a measurable set. So this condition is called the Caratheodory condition. This is called the Caratheodory condition. In fact, later in this course, I will explain to you. I will give you other definitions of Lebesgue measurable set. This is just one way of defining Lebesgue measure. So a set E, this E is said to be Lebesgue measurable. It's said to be measurable if you take a set T in R, a subset of R, any set, that's why I take for all T in R, the outer measure of T is equal to the outer measure of T intersection E plus the outer measure of T intersection E complement. Then we say the set is measurable, or the set is Lebesgue measurable, or it's a measurable set. So after defining this, this is called the Caratheodory condition. Indeed, let's do something. T is actually inside T intersection E union T intersection E complement. So indeed, we have this. T is inside this. It's inside T. It's a subset of T intersection E union T intersection E complement. And if you want to check this, it's very easy to check. T intersection E union T intersection E complement. T intersection from algebra. I have T intersection and T intersection here. I can bring it out and have T intersection. Then I will have E union E complement. E union E complement will give me the whole set R, and T intersection R will be T. So you can see that from what with what I'm saying that indeed or obviously T is inside this one, and by so doing from the property of measure, by monotonicity of the outer measure, with what I explained, monotonicity means that if A is inside B, if A is a subset of B, then the outer measure of A is less or equal to the outer measure of B. That's what this means. So by monotonicity, it means that the outer measure of T, since T is inside all this, the outer measure of T will be less or equal to the outer measure of T will be less or equal to the outer measure of T intersection E union T intersection E complement. And what I'm doing, this is always true. What I'm writing here is always true. So from there, the outer measure of T will now be less or equal to from countable subadditivity. This one will become plus. This one will become, when you have it's addition. I've told you yesterday. T intersection E plus T intersection E complement. So I have this. So it means that outer measure of T is less or equal to the outer measure of T intersection E plus outer measure of T intersection E complement. That's what I'm going to have. So what am I trying to say, or what am I trying to bring out in this case? So if you are told to prove that something is a measurable set, or you should show whether or not a set is measurable or is Lebesgue measurable, you see that you show this. Now, for this one to be equal, for the outer measure of T to be equal to the outer measure of T intersection E plus the outer measure of T intersection E complement, for it to be equal this way, number one is that we have this one will be less or equal to this, and it will also be greater than or equal to this. So from what I have written now, I've shown you that this is always less or equal to this. It's always true. This is always less or equal to this. So in other words, I don't want to write in other words. So so it suffices to also show that the outer measure of T is greater than or equal to the outer measure of T intersection E plus the outer measure of T intersection E complement. So my point is that if you are told to show that something is measurable, it's Lebesgue measurable, it's either you show that it is equal or you show it's greater than or equal. Once you show that it's greater than or equal to this, you are also true, because this one is always true by monotonicity and countable subadditivity. This one is always true. So if we are told to show that something is measurable, you can use this once when you prove and you get to this one, you get this. If you can prove this, then you are true. That means you have shown that it is measurable. Or you show this. They are all Caratheodory condition. So you see that if you show this one, and if you see that it is getting difficult to show that it is equal to, just prove that it is greater than or equal. Once you can prove that it is greater than or equal, or it is equal to, you have proved the Lebesgue measure. You have proved that the set is measurable, it's Lebesgue measurable. So from here I'm going to be talking about some theorems, and we are going to be proving them. We are going to be talking about some theorems in Lebesgue measure and integration. And this one is Lebesgue measure in R. So let's give the first theorem. Theorem 1. The first theorem. The complement of a measurable set is a measurable set. The complement of a measurable set is measurable. Proof. So when you see measurable, we mean the Lebesgue measure, like it is Lebesgue measurable. So I will not be writing Lebesgue measurable every time. So the complement of a measurable set is measurable. It means that the complement of a Lebesgue measurable set is Lebesgue measurable as well, or it's also a Lebesgue measurable set. Now we want to prove. The first thing is that let E be a measurable set. We want to prove that E complement is measurable. So that's what this theorem is talking about. That is, if E is a measurable set, then its complement is measurable. So let E be a measurable set. we want to prove that E complement is measurable. For it to be a measurable set, what does that mean? It means that we will let T be a subset of R, then it means that the outer measure of T is equal to the outer measure of T intersection E plus the outer measure of T intersection E complement. This is what it means. This is what it means. So the outer measure of T is equal to the outer measure of E plus the outer measure of T intersection E complement. That is the meaning of E to be measurable. So in reality, let me show you. In reality, what we want to prove, we want to prove that E complement is measurable. That is, for E complement, that means that for E complement to be measurable, it means that the outer measure of T will be equal to the outer measure of T intersection E complement plus the outer measure of T intersection E complement complement. That's what it means. Whenever you want to prove that something, see, a set E is said to be measurable. This set E is said to be measurable if outer measure of T is equal to outer measure of T intersection E plus T intersection E complement. So as well, if I want to prove that E complement is measurable, it means that the outer measure of T will be equal to the outer measure of T intersection this one E complement plus the outer measure of T intersection E complement complement. So that means that in reality I want to prove that the outer measure of T intersection E complement plus the outer measure of T intersection. So the complement, when you have the complement of a complement, you just have E. E complement is just E. So that means this is what I want to prove. So that means if I can get this, then I have proved that E complement is measurable. So I will have the outer measure of T is equal to outer measure of T intersection. This E is same thing as E complement plus the outer measure of T intersection E complement. So by so doing, it is already obvious that E complement is measurable. Therefore, E complement is measurable. Therefore, A complement is measurable because you can see that T intersection the set complement plus outer measure of T intersection the set is equal to the outer measure of T. So that's why we say E complement is measurable. So the second theorem we want to prove. The second theorem we want to prove is theorem 2. Number 2 theorem. The empty set and the whole set are measurable. Proof. So in reality, I'm working on R, so the whole set is R. I want to prove that R is measurable, and indeed R is measurable because, look at it, let T be a subset of R. What happens is that if I take the outer measure of T intersection R plus the outer measure of T intersection R complement, this one will give me the outer measure of T intersection R is T. Since T is inside R, it's a subset of R. So T intersection R will just be T plus the outer measure of R complement will be empty. R complement will be the empty set. Since it's the whole space, R complement will be empty. So T intersection, the empty set, is empty. So I have the outer measure of T plus the outer measure of the empty set is 0. The outer measure of the empty set is 0. So I will be left with the outer measure of T. So that's what I have. So that means therefore, of course I can show you therefore R is measurable. Why? Because I've shown that the outer measure of T, or the outer measure of T intersection R plus the outer measure of T intersection R complement is exactly equal to the outer measure of T. So that means R is measurable. And again, the empty set is measurable as a complement of a measurable set. As a complement of a measurable set R. So you can see, if you take the complement of R, that is, if you take the complement of R, you have the empty set. So don't forget, the first theorem I proved here is that the complement of a measurable set is measurable. I have proved that R is measurable. So, and since R is measurable, that means it's a measurable set. The complement of a measurable set is measurable, and since R is a measurable set, the complement is the empty set is also measurable. That means R complement will also be measurable from this theorem. And what is R complement? The empty set. So that means the empty set is measurable from this theorem 1. So we have proved that as well. So let's go to the third one. Let's go to the third one, theorem 3. Theorem 3 is saying that, what do I have here? Let E be a set so that the outer measure is 0. Let E be a set so that the outer measure of E is 0. Then E is a measurable set. Then E is a measurable set. Let E be a set so that the outer measure of E is 0. Then E is a measurable set. Now let's prove this one as well. Proof. What do we want to do? Let E be a set. The outer measure is different from measurable set. From measure. We define outer measure to be the infimum of what? Summation of the length of intervals, so that E is inside the union of the intervals. We have done that already. Yes, in the first class. Now, in this case, today I have defined measurement when the set is said to be measurable from the Caratheodory condition that the outer measure of T is equal to outer measure of T intersection E plus outer measure of T intersection E complement. So, but from here, let E be a set so that the outer measure of E is 0. Then we want to prove that E is measurable. That means that, let me tell you, of course, we want to show that outer measure of T. Now, let us prove. The first thing we need to do is that let T be inside R. Right? Let T be inside R. So, we know that the outer measure of E is equal to 0. We know that now, from algebra, T intersection E will be inside E, will be fully contained in E. T intersection E will be fully contained inside E. So what am I trying to say here? What I'm trying to say here is that since I have T intersection E and it's fully contained in E, if you don't understand that one, just take two sets. Let's say A1 is equal to 1, 2, 3, and another set A2 to be equal to 2, 3, 4. What is A1 intersection A2? A1 intersection A2 will be equal to, the intersection is just 2 and 3. You can see, and you can see that A1 intersection A2 is a subset of A1. A1 intersection A2 is also a subset of A2 because 2, 3 is inside A1 and it's also inside A2, so they are both subsets. So whenever you take intersection of two sets, it is always inside either of the sets. So, but here I want to take E. T intersection E is always inside E. So what does that mean? The outer measure of T intersection E by monotonicity will be less or equal to the outer measure of E. What is monotonicity? Don't forget the property of the outer measure I gave to you in the first lecture. Now, number one is that the monotonicity is saying that if you have A and it's inside B, A and it's inside B, the outer measure of A, that's the meaning of monotonicity, will be less or equal to the outer measure of B. So that is what we are talking about. That's what we are saying. So since T intersection E is inside E, it means that the outer measure of T intersection E will be less or equal to the outer measure of E. But from what we are given, the outer measure of E is 0. So this is 0. So it means that the outer measure of T intersection E will be less or equal to 0. Don't forget, the outer measure is not negative. That's the first property I gave to you, that the outer measure of a set is always greater than or equal to 0. That's the first property of the outer measure. So that means that the outer measure of a set can never be 0. Can never be negative. So the outer measure, since I have outer measure of T intersection E to be less or equal to 0, it means that it has to be 0, because it can never be negative. Outer measure is never a negative value, so it has to just take 0. It can never be less than 0. It has to be 0. So that means that the outer measure of T intersection E will obviously just be equal to 0 exactly. That's what we are going to have. Now, for the second one, I've proved this. Let's call this 1. I've proved that the outer measure of T intersection E is equal to 0. Now, come to this one. T intersection E complement is also inside T. The outer measure of T intersection E complement will also be inside T. And what does by monotonicity again? It means that the outer measure of T intersection E complement will be less or equal to the outer measure of T. If I should rewrite this, then I have the outer measure of T to be greater than or equal to the outer measure of T intersection E complement. This is what I have, outer measure of T. If I rewrite this, outer measure of T will be greater than or equal to outer measure of T intersection E complement plus 0. Anything plus 0 is still the same thing as that thing. So, but 0 is equal to the outer measure of T intersection E complement. So, this 0, I can just, so that means I would now have the outer measure of T will be greater than or equal to the outer measure of T intersection E plus the outer measure of T intersection E complement plus the outer measure of T. And I'm true. I told you that it's either I show equal to or greater than or equal to. So it means that the outer measure of T is greater than or equal to the outer measure of T intersection E complement plus the outer measure of T intersection E. And that's the Caratheodory condition that says that that's the Caratheodory condition that for a set to be measurable, this has to be satisfied. And since we have already satisfied that, therefore, thus E is a measurable set, or E is measurable. E is a measurable set, or E is measurable. Number four, a countable set E of real number is of measure 0. A countable set E of real number is of measure 0. So now, proof. Let us define the countable set. Let it be equal to xn such that n is in n. This is a countable set. A countable set means a set you can count. You can count. It can be finite. It can be infinite. So by so doing, by writing this means that means I have x1, s2, s3, s1. It goes on like that. That means this is a countable set because you can count it. So or you can another way of finding a countable set is that you can map it to a set of natural numbers. You can map it to a set of natural numbers, or the domain can also be a set of natural numbers and they'll be mapped to all these values. So, but let E be equal to the to be equal to this. We want to prove that. The measure of E is 0. We want to prove that the measure of E is 0. So the first thing we are going to do is that we find an open cover. So later I will still explain to you. I will still define the value of a measurable set. So that condition I gave you is just to check, or is just to prove. That Caratheodory condition is just to check or prove that a set is measurable. But if you want to get, once the set is measurable, then if you want to compute the value of the set or the measure of the set, if you want to compute the measure of the set will just be equal to the outer measure of the set. So if you want to prove that the measure of E, you can say I did not put star. The mu star is outer measure, while mu is just measure. We want to prove that the measure of E is 0. But meanwhile, the measure of E, once the set is measurable, the measure of E will be equal to its outer measure. So we have that. We take an open cover. We say obviously or indeed E is covered by this set. E is covered by the union of Sn of the interval Sn minus epsilon over 2n plus 1, comma Sn plus epsilon over 2n. Yes, you will see the reason why I put over 2n plus 1 over 2n plus 1. So where this range is n is starting from 1 and it goes to infinity, E is fully covered by this, by the union of this. So now what happened is that E is covered by this, you can see, because every open interval will contain S. Every open interval will contain what's it called, a term here. So you just shift it. If this is S1, say this place is S1, then you now open an interval. So this S1 will now be what you have opened here. The distance between here and here will now be this epsilon over 2n plus 1. Then the distance between here will also be S1 plus epsilon over 2n plus 1. And you do like that for all of the elements in that set, in the set E. So it covers E. And by so doing, we know that before I go far, let us compute the measure of this one at the length. The length of the union of n starting from 1 to infinity of the length. Let's calculate the length of Sn minus epsilon over 2n plus 1, comma Sn plus epsilon over 2n plus 1. We want to do this. This one will obviously be equal to, the union will come out of the length. I told you whenever union come out, it will become summation. Summation of n starting from 1 to infinity of the length of this. Since this is an interval, then the length will just be equal to, when you have length of interval a comma b, will actually be equal to b minus a. Length of interval a comma b is just b minus a. So that means length of the interval, all this one will just be Sn plus epsilon over 2n plus 1 minus, this one is like b minus a, minus Sn minus epsilon over 2n plus 1. So at the end of the day, by the time you compute this one will be equal to summation of n starting from 1 to infinity of what you'll be left with here will be Sn minus Sn will be 0. Epsilon over 2n plus 1 minus times minus will be plus epsilon over 2n plus 1 will be 2 epsilon over 2n plus 1 over 2n plus 1. Continue. So this one at the end of the day will be equal to the measure of n starting from 1 to infinity of epsilon over 2 raised to power n. Epsilon over 2 raised to power n. So by so doing, you will see that this one will give us exactly epsilon. So what happened here is that epsilon actually come out, n starting from 1 to infinity of 1 over 2 raised to power n. Let me just explain to you. So I need to explain to you that this is 1, that this one is 1, is 1. So let me show you. If I'm to write this, n starting from 1 to infinity of 1 over 2 raised to power n, this is 1 over 2 plus 1 over 2 square plus 1 over 2 cube, and it goes on like that. That's when this is a GP. It's a geometric progression where the first term a is 1 over 2 and the common ratio is also 1 over 2, and since the common ratio is less than 1, we can compute the sum to infinity. So we just compute the sum to infinity, which is a over 1 minus r. A is 1 over 2 over 1 minus r. R is also 1 over 2. So 1 over 2, everything divided by 1 minus 1 over 2 is also 1 over 2. Half divided by half will give 1. So that's why this one is 1. So whenever we have something like this, everything over 2 raised to power n, the value is always 1. So you now be left with epsilon. So epsilon. So we have epsilon as the answer. So so next time I will not be showing all this. You can easily compute that and you see that the answer will be 1. So now that's epsilon. So that means that the length of all these ones, the answer is epsilon. So that means, so now the outer measure of this one, the outer measure of E. Don't forget, since this is the open cover, and this is the open set that cover E. The outer measure of E from definition is the infimum of the summation of the length of n starting from 1 to infinity of the length of this, of the length of Sn minus epsilon over 2 raised to power n plus 1, comma Sn plus epsilon over 2 raised to power n plus 1, so that E is inside the union. So that E is inside the union of n starting from 1 to infinity of xn minus epsilon over 2n plus 1, comma Sn plus epsilon over 2n plus 1. That's what we are going to have, so that the outer measure of E will be equal to the infimum of summation of n starting. So the summation of all these ones, we've done that already, which is length of this one. This is what we are going to have. The summary is that all these ones will become epsilon. We have already computed it, calculated it. So the infimum of epsilon, so that so this one, the infimum of the answer is for this one is epsilon. So I have E is inside the union of n starting from 1 to infinity of xn of Sn minus epsilon over 2n plus 1, comma Sn plus epsilon over 2n plus 1. So that's what I'm going to have. So and what does that infer? That means that the outer measure of E is 0. If you take the infimum of epsilon, don't forget, from the definition of infimum, when you just have epsilon here, then that means the outer measure is 0. Don't forget, if the outer measure of a set is 0, then the set is measurable. So since the outer measure is 0, the set is measurable. So the outer measure of, from what I have calculated here, that means that the outer measure of this countable set E is 0. But since the outer measure is 0, see, if let it be a set so that the outer measure is 0, then the set is measurable. So since the outer measure is 0, it means that the set will be measurable. So if the set is measurable, the measure of that set, measure of E, will be equal to its outer measure. So since it is equal to its outer measure, that means measure of E is also 0. So that means a countable set E of real number is of measure 0.